So today we're going to take a look at the next week's lab, molar mass of a volatile liquid. We've done molar mass by one other method. Do you remember what that was? We titrated an acid. Acid-base reaction to find the molar mass of citric acid. We did do that, didn't we? It's in my schedule. This time we're going to get the molar mass of a compound that is normally a liquid at room temperature, and with just a little bit of heat we can volatilize it and fill a space. So we're going to be using gas laws to find out how many moles of this gas we have. All right, this method was developed by a Frenchman. Let's see if I can spell his name. Dumas. Now that's not to be confused with the Three Musketeers Dumas. That's Alexander Dumas. This is a chemist, physicist, and he worked in the first part of the 19th century. Well, Alexander Dumas wrote about that time also, so the Dumas must have been everywhere. Anyway, what we want to do with this method is determine the molar mass, and remember, to find the molar mass, and that's my abbreviation for molar mass, is we need the mass and the number of moles associated with it, just like any other determination. Right? The mass is fairly easy to get. We're going to have a 125 milliliter Erlenmeyer flask, and this whole volume is going to be filled with the gas at a known temperature, a known barometric pressure. We're going to determine the volume, the exact volume in this flask, because 125 is up here somewhere. You need the entire volume, right? And it's in the neighborhood of 145 milliliters. So if you know the temperature, and you know the volume, and you know the pressure, and you can find the moles, right? All you need is the ideal gas equation. Okay, we know that one, that one, that one, and this is a constant. We can find the moles. Okay, so you know the moles by this method. And then how do you get the mass? Well, you weigh this thing with any additions that you put into it. We're going to have a cap on it. So you have to have all that together before you conduct the experiment. And then afterwards, you weigh the whole thing again. So it's by difference. You know the mass before, you know the mass after, and then you can get the mass by difference. And once you know those two factors, molecular weight is simple. Now the method combines all this into one equation. And it does that by taking this one and solving this one for moles. So if we solve this one for moles, we get mass over molecular weight. They use just a capital W, a capital M. I don't like using just a capital M because that could be molarity. So I go back to my roots. We used to call molar mass molecular weight. That's why MW. So once you solve it for that, you can insert this expression right here. Okay, times RT. And then we can solve for this one. So just bring this one over here. and bring these two over here. And you can solve the molecular weight in one equation. Or you can do it in two. It doesn't matter really. But with one calculation, you can get the molar mass of this gas. Okay. So that's the whole gist of the experiment. We've got some pre-lab questions we can do. You rather do the pre-lab questions or talk about the procedure again some more? You've had a chance to look at the procedure, I said. Wishful thinking on my part, right? Some of you have. Okay, well, since I've got the drawing up here already, let's do the procedure. So we've got this 125 milliliter Erlenmeyer flask. And we're going to have a sheet of aluminum foil, and then we're going to have a bigger sheet of aluminum foil. 2 sheets of aluminum foil. We're going to have a rubber band, right? And we're going to have copper wire. And what you want to do is when you weigh this flask on your balance, this goes on the balance, what goes with it? Well, you need the flask on the balance. You need the small aluminum sheet. Okay. You need what's holding that aluminum sheet down, which will be the copper wire. Okay, you need those. You don't need the big sheet or the rubber band, because when you weigh this the second time, only these items are going to be on the flask. These will be removed. Okay, you're probably wondering, if you haven't read the method, why do you need 2 sheets of aluminum? Well, when you put the small sheet of aluminum on here and cinch it down with a copper wire, then you're going to cover that with a bigger sheet of aluminum with a rubber band. The reason you do that is you want to protect this part of the contraption from water condensation. You don't want water to get up underneath that one. So you protect it with this one. But it's not going to be weighed. It's just there to protect it, because you're going to take this flask and you're going to clamp it. Not jet clamp it, just you're going to clamp it to a ring stand. Okay. So you're going to clamp it to a ring stand and submerge it in your water bath as far as you can get it in there. You want as much of this in the water as possible without getting this part in the water bath. But it's going to be boiling. And so you can, and vaporizing, you're going to get condensation all over this big one. So once you vaporize the liquid, that you got this one here and you got the big one here, you got a liquid down here, and it's going to vaporize into a gas. And you got a pinhole punched in the top of it to let the vapors out. And it also drives out any air that's in there. So the only thing you want in this flask is the liquid vapor. That sounds like contradiction. Vapor derived from the liquid. So once we waited long enough for all of this liquid to vaporize and this whole cavity is full of the vapor, then you can take it out. Of course, you're going to measure the temperature, right? You're going to measure the temperature. You're going to have the barometric pressure, temperature, pressure. You're going to have And then you're gonna get the mass, after you pull it out and towel dry it, and then pull this big one off, pull the big aluminum sheet off, then inspect the top of it to be sure that you don't have any condensation on it. Because if you do, and you weigh it like that, that makes you think that you've got more gas in there than you really do. And the gas that's in there is going to condense, which is fine. Because mass is mass no matter what the phase is. Okay, so you're going to weigh it before, weigh it after, get the difference for your mass. And you're going to need the temperature, you're going to need the barometric pressure, and you're going to need the volume. So how do you get the volume of this flask? Well, yeah, there are two methods, and take your pick. You can fill the flask up, with water all the way to the top where it's right there. The same place where the little aluminum foil is flush across the top. That's what you want. And then you can pour it into a graduated cylinder and measure the volume. Okay, that's one way. It's not very accurate, but it works. The other way is get the mass of this flask before you add anything to it, just a dry flask. And then fill it up with water and get the mass again. So you can get the difference in mass, and you can use density the density of water at that temperature, whatever the air temperature is good enough. The density, and you know the mass, you can calculate the volume. Okay, and I think there's a chart in the method with the density of water at different temperatures. Could be. Let me see if it's still there. Oh, this is my key. It may not have it in this one. It's in yours. Yeah, that blue. Yeah, that's it. So all you need is the exact temperature of the water, and you can get the density from that chart. And you weigh before and after, get the mass. Then you can, and I would do this after the experiment. Because when you put water in there, it's going to be kind of hard to get it out. You want a dry flask when you do this part of the experiment. So do this first, then do this second. If you want to, well, either way, you're going to put water into it. So do this one second, whether it's this way or that way. Okay. And all you have to do is when you write up your report, say which way you did it, because you're going to have to give your data for determination of the mass if you do it this way, excuse me, the volume if you do it this way. Or you just say you measured it in a graduated cylinder if you do it that way. Okay. So now we've got all the data we need from the experiment. What do we do with it? I think pre-lab questions ought to come next. Any questions before I start erasing all this good stuff? No? Okay. What did they use on the board last night? There it was. Stripped opened up a lot of pockets for the ink to hide. And leave a can of WD-40 out here as a hint. It works. Okay, pre-labs. Number one. Let's see. I should, since this is being recorded, let me scroll down to the pre-labs. Here we go. What happens to a real gas like Yeah, nitrogen is our example here. What happens to a real gas as it cools from room temperature to 0 K? I wouldn't say to 0 K because you can't get there. But towards 0 K would be a better choice of words. As you approach 0 K, absolute zero, what happens to a real gas? As we approach, trying to remember. Yeah, I think they just write this. The limit of gas as you approach 0 K. That's calculus. First thing you study in calculus is limits. So what happens to a gas as it approaches 0 K? A real gas, it is. Okay. Well, let's start with an ideal. What happens to an ideal gas as you approach 0 K? Nothing. Stays a gas all the way down to the bottom. Yeah. How about real gases, though? What do? Sometimes they'll turn to a solid. Yep. Yeah. There are a few of them that stay liquid all the way down. But there are a few that turn solid. Right? Carbon dioxide is a good example. You can make a liquid out of it, get it cold enough, and then colder still, you can make a solid, dry ice. Yeah. So at the very least, it condenses. Would you expect it to disappear when it reaches absolute zero? No. If it's an ideal gas, yeah. That's one of the assumptions of ideal behavior in gases, is the gas really isn't there. It's just the space that matters. But real gases, yeah, the mass is still there. And it's a good thing it is. Otherwise, this method won't work. If there's no mass there, you can't weigh it. Okay, that was one. How about number two? See, is it showing? Yeah, 2 is showing. What are the units of the universal gas constant? Okay. For our purposes, what are the units? Right? Think of, we're going to have pressure, volume, moles, and temperature. So pressure will be in atmospheres, right? Volume will be in liters. This is moles. And this is K. Right? So the units of R are liter atmosphere per mole K. And then all you have to do is put PV equals N, and that's RT. To prove it to yourself, if this is K, that's denominator, numerator that cancels. This is moles, right? Moles cancel. Liters on this side, atmospheres here. They're in the numerator on both sides, so that means this would be on the denominator on that side, so those cancel, those cancel. So we got the right units of measure for R, liter atmospheres per mole K. Is that it? That's it for 2. The reason I went to all that trouble was, depending on what equation you're using, R could be something different. If we have joules per mole K, some require that one. It'd be a different value, 8.1345, I think, something like that. So in our case, those are the units of measure. How about this one? 3. Water freezes at 0, 32, and 273. They add 0.2 there. Water freezes at those temperatures. Which one's right? It's a trick question. They're all right, right? They all, each one of these describes the same physical phenomenon. It's like I've always said, nature just does what it does. And this is the way we describe it. If we're in these units, it's that one, those units, that one, those units, that one. It's all the same. Right. And neither one's colder than the other. They all describe the same phenomenon. Yeah. I should classify that under another trick question. Okay, number 4. When can a real gas behave as an ideal gas? And are those conditions met in this experiment? When is a real gas like an ideal gas? I think we covered that in class, didn't we? What are the conditions that approach ideal behavior for real gases? Has to do with temperature, right? And pressure, yeah. High temperature, low pressure. And I added one, low moles. What you're getting at with all of these conditions is you want to minimize intermolecular forces. You don't want these gas molecules to be attracting each other, repelling each other. Right, so if you have very few of them, the opportunity, the probability they're going to interact is lower. If the pressure is low, well, these go together. If the pressure is low, it means you don't have much in there. Large volume for the same amount. And high temperature means that they've got so much kinetic energy, when they do impact one another, they're not together for very long. And the energy of impact overcomes any intermolecular forces that may be attracting or repelling. Right, so you minimize these forces, and that gives you ideal behavior. Are the conditions met for us in our experiment? Well, high temperature relative to what? Well, relative to 0 K. Yeah, 270 degrees, 3 degrees higher than 0 K. Okay, yeah, that's right. How about pressure? 1 atmosphere? That's relatively low pressure. Now, this is for gases that are gases at room temperature. Now we've got a little bit of a tweak to our situation because these are liquids at room temperature. We're heating them up, so we're adding temperature, and that's good for ideal behavior. But if you don't get it significantly higher than their boiling point, then you may still get some interactions that could skew your results. Okay, so we always be mindful of that. And low moles, yeah, once you get it in the gas phase, this is guaranteed. Okay, so essentially we've met the conditions. All right, that was 4. And 5. 5 is an actual calculation that we're going to do. A simulated experiment. A gas with a mass of 33.62 grams. 33.62 grams. That's going to have to be a lot of gas to weigh that much. And it occupies a 10-liter flask. So volume equals 10 liters. Okay, that makes more sense. Got a lot of gas, it can weigh that much. At 27 degrees C. Okay. We know we're going to need we're gonna need K, so we might as well go to. And what else are we given? 730 torr. What's a torr? It's a millimeter of mercury. Right. So we need our units need to be atmospheres. Let's see. Torr per atmosphere. Okay. So let me go ahead and crunch the numbers there. 730 and 760 is 0.9605 atmospheres. Okay. Now, do we have enough information? What's the molar mass of the gas? Okay. So we can either do it in 2 steps, or we can use that formula. Remember, molecular weight equals, I have to look, I don't remember. Equals. Oh, I see. Mass times R times T divided by P times V. Okay. So, molecular weight equals 33.62 grams, and R is 0.08206 liter atmospheres per mole A, and temperature is 300 divided by 0.9605 atmospheres, and volume 10 liters. Here we go. So let's see. Denominator, numerator. Yep, that's good. Denominator, numerator. Yep, that's good. K, denominator, numerator. That's good. So this is going to be, yeah, mass per unit mole, denominator, numerator. That should be good. So that's the thinking part. The rest is number crunching. 33.62.08206. And this value is in useful information. You don't have to remember that. Times 300.9605 and 10. So I get 86 point C. Oops. 3 significant figures. So 86 grams per mole. Okay. I think that's the last. Yep. Okay. Any questions so far? Let me see. We got any post-lab questions? Well, you'll see in this chart right here, I've got 1, 2, 3, 4, 5, 6 different volatile liquids to choose from. And they each have a number on them. I don't put the names on them when you pick them off the cart. You just pick the one you want and just note the number. And some of them have a distinctive odor. So you could sniff them and say, I think that's this one. But you need to do the molar mass to prove it. Let's see. Yeah, post-lab questions. I probably shouldn't do these for you because we haven't done the lab yet. Let's see. Right, that only took 30 minutes. We'll just talk about it a little bit. Get you thinking. This first one. Let me scroll down so anybody viewing this later will be able to see the questions. So how would you calculate the volume occupied by 1 mole of gas at 1 atmosphere and 0 degrees C? Known as, that's standard temperature and pressure. 1 atmosphere is 0 degrees. For gases, 0 degrees C is standard temperature. Everything else, standard temperature is 25. Don't ask me why. So how would you calculate the volume? Just take the ideal gas equation, solve it for volume, and plug the numbers in. Wouldn't you? And you can tell me what the volume of 1 mole of gas at 1 atmosphere and 0 degrees C would be. Let's see, 2, we've already talked about that. We won't beat that horse anymore. Okay. So for number 3, we've got several different types of errors that may be introduced. Explain how each affects the results. Heating was stopped before all the liquid in the flask had evaporated. What would that do to the calculation? Yeah, give you a higher mass. So a higher mass divided by moles. Higher mass would bias it in positive direction. You would have an erroneously high value for molecular weight, would you? What if water remained on the outside of the flask and on the foil when the final mass was determined? Same thing, right? You've got extra mass that's not the gas. How about C? The volume of the Erlenmeyer flask was assumed to be 125 milliliters and not actually measured. Okay, so that takes a little more work. Let's use that equation, that overall equation. Go back to the front. And let's see, it's on the second page. Okay, so if we're doing molecular weight equals mass times R times T divided by P times V, then what effect would C have on it? The volume of the Erlenmeyer flask is more than 125. Okay, it's more than 100. But if you put a value here that's less than 125, what would that do to the answer? This is in the denominator. If you put a value that's lower than it should be here, yes, right? When the denominator is lower than it should be, the quotient value is higher.
Like the whole number.
It do what?
If it's lower on the bottom and higher on the top, it'll be a whole number.
Oh, if you have two factors going on at the same time. Yeah, if you have lower here and high here, it depends.
Yeah.
If the ratio between the two is 1, it won't have any effect. But if the number up here is higher than the number down here, then the ratio would be more than 1, would increase this and vice versa. Yeah. All right. Let's see. 4. Student has an unknown liquid and determine its molar mass by collecting data as described in this experiment. So the mass of the Erlenmeyer flask is 79.621. This is with the foil and the copper wire, the inner foil, smaller one. And the mass of the cool flask containing the condensed liquid is this value. So what's the mass of the flask? Just the difference, right? Just take the difference. Temperature of the boiling water is 99.5. Yours is probably going to be less than that. Probably because we're at higher altitude. The volume of the flask. Oh, they're given the volume, 130.3. That's a little low. But it's part of the problem. Atmospheric pressure, 727 torr. You need to convert it to atmospheres, right? Okay. And use that data to calculate, and then determine, using that value, which gas do you have? And so we look over to page 3, I think it is. No. Page 5. Page 5. Then you take that value that you get and look here and see which one it is. That's it, isn't it? That all posted? Yeah. So all you have to do after that is show me your data, calculations, tell me what gas it is. Now, what happens lots of times is for some of these gases, like I said, you can sniff them and say, I think it's this one. But when you do the calculation, it tells you something else. So if it does that, then you've got an explanation to make. Why does it smell like isopropanol, right? Rubbing alcohol, but the value, the molar mass, doesn't say that. It says something else like pentane, acetone.
To convert that toward their atmosphere, you divide it by 760.
Yeah. So we have, let's say we have 724. Oops. And we use our dimensional analysis to convert it. We need to cancel torr, right? And leave us with atmospheres. So what's the ratio here? 760 to 1. That's why 760 divided into 720 gives you that value. I just took a shortcut.
Yeah.
I wasn't springing anything new on you. This is chemistry. This is not a mystery religion. Okay. I guess that's it then, unless you have questions. We have this one and this is it. This is the last lab. Yeah, there are only 7 labs. So from after next Tuesday, we won't have any more labs. Okay. You just have time to pretty this one up. Let's see. That means I needed to give you a date that this one is due. April 25th. Yeah, April 25th. So that's a couple of weeks. Yeah. I've tried running labs before, right up to the end of the semester, and it always ends in disaster. So I cut them off early. We just hit the ground running first day of class, and then we've got more buffer at the end that we can, if we have to shift anything, then we've got room. And that works for lectures too. I'd rather slack up later than slack up at the beginning and have to